This is part D of grade 4 practice paper 2. It is the end of the practice paper, and we know that the end of each practice paper has also problems that are not multiple choice, but we have essay type answers included at the end. So we will continue, go through all of the multiple choice problems and continue to the 3 essay type problems that are at the end. Number 37. N divided by 5 and the result is 10. Then n equals, what number do we divide by 5, Jerry, and the result is 10? We divide that number by 5.
50.
And Jerry is saying that it is 50. And he is correct. N divided by 5 and the result is 10. Then what number do we divide by 5 and the result is 10? That number is 50. So we are magnifying the statement that we have there, the arithmetic statement that we have there. We have an equation to solve. What number do we divide by 5 and the result is 10? If we can cancel or eliminate 5 from that left hand side, then we can find n. We are dividing by 5. We may eliminate 5 by doing the opposite of divide, which is multiply. The process may be more obvious if we replace the division sign with n over 5. So sometimes when we have a mathematical problem to solve, we may convert it to a form that is convenient to us. And in this particular case, it might not be convenient to all. As a matter of fact, it does not matter because Jerry would have found the answer already. But let us convert that to a more visually friendly form. So we have n over 5, or n divided by 5. We need to eliminate that 5 that we have there dividing on the left hand side. And we will eliminate the 5 that we are dividing by multiplying by 5. But because this is an equation, we have to treat both sides equally. What we do to one side, we will have to do the same to the other side. So we are multiplying by 5. So we are multiplying by 5 in order that this 5 can be cancelled. So we have to multiply by 5 on the other side, irrespective of the consequence of multiplying by 5 on that side. So with the need to eliminate 5 from that left hand side, 5 is being divided, so we eliminate it by multiplication. The 5s will be gone. The 5 that we started off with, dividing the n, will be gone. But we have to treat both sides equally. Therefore, when we multiply the left hand side by 5, we will have to also multiply the right hand side by 5, Jerry. Irrespective of what happens on that right hand side. 5 is cancelled from the left hand side, and on the right hand side we have 10 multiplied by 5. So 5 is cancelled from that left hand side, and on the right hand side we have 10 5s. 10 5s, Jerry?
50.
Right. The correct answer is therefore option
D.
n divided by 5 is equal to 10. In solving the equation, we may consider that if there is some number that we divide by 5 and the result is 10, then that number must be greater than both 5 and 10. We divide a number by 5 and the result is 10. That number has to be greater than both 5 and 10. And that is logical. It makes sense. That's a common sense approach. It is logical to say that n must be the result of multiplying 5 and 10. 5 tens, 50. How do we know that since n is larger than 5 and 10? The correct approach will not be to add them. As a matter of fact, even at the higher level, students make mistakes like that. The unknown in the equation is divided by something. In order to eliminate that thing, students add. Choosing add to be the opposite of divide. And we know that that's not correct. The correct answer is therefore option D. If that is not satisfactory, then we may take the original equation and replace n with 50 and see if the result is 10. Because we are saying that n is equal to 50. So we can take the original expression, n divided by 5 is equal to 10, put 50 where we have n, because we are saying n is 50, and see what happens. If that is not satisfactory, let us say n divided by 5 is equal to 10. That's our original expression. And what do we do there? We will replace n by 50. Is it true that 50 divided by 5 is equal to 10?
Yes.
Right, that means n is actually equal to 50. 50. We have confirmed our answer. Mathematics is good for reconciliation, but make sure that you can solve problems by applying fundamental principles. So we do not want students to have the notion that if n divided by 5 is equal to 10, then they need to substitute in these values for n. Say n is equal to 2, see what happens. Say n is equal to 5, see what happens. Say n is equal to 15, see what happens. Say n is equal to 50, and see what happens. And then, when we divide 50 by 5, we get 10. That is our answer. Then we say, hurrah! That is our answer, and we are correct. Students need to be able to solve problems by making use of fundamental mathematical principles. N divided by 5 is equal to 10. What is n? Going back to the original method of solving the problem and go as far as replacing the division sign with the fraction bar. Some candidates might want to eliminate the intermediate step. So, students solve this in one step. N divided by 5 is equal to 10. N is equal to 10 times 5 is equal to 50. They will still consider that they are multiplying both sides by 5, but they will not write it down. Instead, they will say that multiplying both sides by 5 will cause 5 to be eliminated from the left-hand side, but on the right-hand side, it will be used to multiply 10. As like that, because it is erroneous to say that since we are dividing by 5 on the left-hand side, we multiply by 5 on the right-hand side. That is a consequence, but that is not what took place exactly. What is it that took place exactly? We multiply both sides by 5. 5 is eliminated from the left-hand side, and on the right-hand side, we need to complete the multiplication process. n is equal to 50. The correct answer is therefore option D, which shows an angle that is greater than a right angle. Which one of those angles is a right angle, Jerry? Is there a right angle in the diagram?
Yes.
Which one of them is the right angle?
Option C.
Option C. Which one of those angles is greater than the angle in option C?
Option D.
That's your correct answer, Jerry. So the examiners have caused this problem to be simplified. How do they do that? They have done that by ensuring that their reference angle is in the option, which shows an angle that is greater than a right angle. What is the right angle? This one in option C. Which one is greater? Option D. That's all there is to it. There is a right angle in the options. Our reference angle is therefore in the options. Or we may say that it is among the options. There's a right angle there. Option C is a right angle. There it is. A right angle is equal to how many degrees?
90 degrees.
90 degrees. It is a quarter of an entire revolution, and it is the one that is marked with straight lines instead of a curve. So notice that your right angle, straight lines. All other angles, curve, curve, curve. So there we have the straight lines instead of the curve. Greater than a right angle. Which one is greater than a right angle? Which one of those angles is greater than one that we have in option C? Which one is greater than the one that we have in option C? The angle is in reference to the open space between two line segments. Therefore, which one has an opening that is greater than the one that we have in option C? So there we have the openings, marking the openings so that it is more obvious which one of the openings is greater. Which span is greater than the one in option C? Which span is greater than the one in option C? The one with the greater opening is option D. That is the one with the greater opening. We may think of an angle as two line segments clasped together, then opened, like we will see in the diagram. So there we have the two line segments together, but because they are together, they look like one line segment. So there we have opening like that. So we actually have two line segments, but because they are at the same location, they appear to be just one. So when we open, we see that we in fact have more than a single line segment. So we open like that, and that opening or that span or that turn that we have there is a 90 degrees opening or span or turn. Right angle. 90 degrees angle is a right angle. The line segments are opened to a right angle. Which one in the option has a greater opening than the one that we have there? And we say that it is option D. The one with the greater opening is option D. Students are expected to be able to identify a right angle at sight. And not only that, but you also need to be able to identify the way that we label a right angle. we are also expected to be able to judge just by looking whether an angle is greater or smaller than a right angle. So we need to be able to identify a right angle, and we need to be able to judge whether an angle is larger or smaller than a right angle. Also, we need to be able to just look and know that when an angle is labeled like this, marked by using straight lines or straight line segments, that that angle is a right angle. It is a 90 degrees angle. It is the angle of perpendicular lines, and it is the angle of a quarter of a revolution. Which statement best tells about the following shapes? So which statement best tells about the following shapes? They both have only straight lines. So which statement best tells about the following shapes? A, they both have only straight sides. They both have only curved sides. They both have straight and curved sides. There is no straight line in any of these shapes. Which one is correct, Jerry? Is it this one? Look at those two diagrams that we have there. Is it true that they both have only straight sides? Do they have only straight sides?
No.
No. They both have only curved sides?
Yes.
All of the sides are only curved?
No.
Okay. They both have straight and curved sides?
Yes.
Okay. There is no straight line in any of the shapes. Do we have straight lines in any of the shapes?
Yes.
Okay. So the correct answer is therefore
Option C.
we may show that on the objects there are sides that match with straight lines. So we have our straight lines going up and matching with the straight sides of the objects. So we cannot say that no straight side is there. And can we say that it has only straight sides?
No.
Let's see. Both objects have straight sides. There are sides that do not match with straight lines. Right, so we have right there this curved sides right there. Curved side right here. Here is also curved. Here is also curved. So we have there sides that do not match with straight lines. So we have sides that match with straight lines, and we have sides that do not match with straight lines. Both objects have sides that are curved. They both have curved and straight lines. Option C is correct. They have both straight and curved sides. So option C is correct. Children in grade 4 should be able to look at lines and make a reasonable enough judgment whether they are curved or straight. So even without matching with straight lines, students should be able to look at lines or line segments and tell if they are straight or they are curved. Four students each drew one of the following shapes in a book. Which two students have similar shapes, Jerry? Which students have similar shapes?
X and Z.
X and Z. So Jerry is saying X and Z, and he is identifying them immediately. So there's no difficulty with that. But When we say similar in mathematics, it goes beyond just looking and say this one looks like this one. Similar in mathematics means similar geometric features, and not that they are identically the same. Similar in mathematics means similar geometric features, and not that they are identically the same. For similar objects, though, the angles are usually identical. For example, those right angles in figures X and Z. And for those who want to say Z, because that's the letter that I knew. I'm almost 105 years old, so I know Z. You do not know anything about Z, Jerry, because you are just maybe 8 or 9 years old. So you do not know anything about Z. Leave that to me. I am 100 and approximately 105 years old, so I know about Z. At this stage, your spatial awareness is coming into question. You should be able to look at objects and determine which of them are essentially the same. For similar objects, the angles are usually identical. For example, those right angles in figure X and Z, figures X and Z. At this stage, your spatial awareness is coming into question. You should be able to look at objects and determine which of them are essentially the same. And Jerry did that without any shortcoming, without any hesitation. He did that not instantly, but instantaneously. We all should be able to say that X and Z are essentially the same without dabbling with other objects. Option D is therefore correct. I will not dwell much on what makes the others incorrect. I will explain what makes X and Z correct on other slides. Why X and Z are the ones that are similar. If two objects exist in such a way that one represents a lateral inversion of the other, then they are similar in shape. If two objects exist in such a way that one represents a lateral inversion of the other, then they are similar in shape. So there we have that one and that one. So if one is a lateral inversion of the other, then they are similar in shape. What do we mean by laterally inverted? That it is flipped over with the mirror line being the center, just like flipping over the page of a book. One is a lateral inversion of each other, then they are similar. There's another similar one. What do you notice about the shape in this particular case, Jerry? What do you notice?
There are several. They're from small to large.
Right. From small to large. It means that it is getting larger each time. It is called a size transformation, which is an enlargement because it is getting larger. If an object is an enlargement or reduction of the other, then they are also similar. So if one object is the enlargement or it is a reduction of the other, then they are similar. So are these two similar, Jerry?
Yes.
They are similar because one is an enlargement of the other. If one object is a rotation of the other, then they are also similar. If we combine the transformations, rotation, reflection, and enlargement, they are still similar. So as long as we use any or any combination of these transformations, these are called transformations. What do we call a transformation? A transformation is merely a change. And the change may be in size, in location, in orientation. As long as there is a change, then there is a transformation. This transformation is a reflection. This one is a size transformation, and this one is a rotation. These, we have other transformations because we have shear and stretch and other transformations. But these transformations, reflection, size transformation, rotation, an object and its image are similar for these transformations. Any change that an object goes through, as long as the shape remains exactly the same, then the objects are similar. Any change that an object goes through, as long as the shape remains exactly the same, then the objects are similar. They are similar. Now, what causes an object to be similar to its image? Notice that we have corresponding angles there. Those two angles correspond. What do we notice? We notice that corresponding angles are equal. In similar triangles, corresponding angles are equal. Although the size changed, the angles did not. The objects are still similar. So in the first one, any change that an object goes through, as long as the shape remains exactly the same, then the objects are similar. And how do we know that the shape remains exactly the same? Because we can match corresponding angles to say that they are equal. As a matter of fact, we do not need to match all three pairs of angles, but we know that if these two are equal and these two are equal, then the other two must also be equal. So as long as the shape remains exactly the same, then the objects are similar. In similar triangles, corresponding angles are equal. Although in this case the size changed, the angles did not. The objects are still similar. Because corresponding angles are equal, we know that the shapes are exactly the same. If there are two triangles with corresponding angles, no matter their size or how they are arranged, they are still similar. So if we have two triangles like we have here and here, and we have this angle is equal to this one, and this one is equal to this one. It does not matter how the shape is arranged on the paper. If it is upside down, if it is laterally inverted, if it is larger or smaller, it does not matter. As long as we can match up or pair up two pairs of angles that are equal, or find corresponding angles that are equal, two pairs that are equal, then we know that the other must also be equal. So the shape is exactly the same. And not only that, that represent similar triangles. So the angles are similar as long as we can find two pairs of corresponding angles that are equal. If two are equal, then the others will automatically be equal. But it is only necessary for us to identify two pairs that are equal. That is our lateral inversion or our reflection. There is a relationship between objects that is stronger than similarity, and that relationship between objects is called congruence. If objects are congruent, then they are the same in all respects. Are they the same in some respects if they are congruent?
Yes. No.
They are the same in?
Some. In all respects.
Right, they are the same in all respects. If that is the case, then they are congruent. So, a stronger relationship than similarity is congruence. For the reflection, size did not change, so they are congruent. For the enlargement, size changed. They are of different sizes and are therefore not congruent. So the first ones, these triangles are congruent because they have what? Corresponding angles, and they are of the same size. These are of different sizes. So although they are similar, they are not congruent. If objects are congruent, then they are similar. But similar objects are not necessarily congruent. If similar objects are of different sizes, they are not congruent. So congruence requires that the objects are the same in all respects, which means that they will have to have the same, size. If 16 blank 4 is equal to 12 is true, then which sign must be where the blank is? And the blank is in the shape of a very minute square. So if 16 blank 4 is equal to 12 is true, then which sign must be where the blank is? Is it multiplication?
No.
Okay. Is it addition?
No.
The first two operators, A, multiplication, and B, division, will serve to increase the value of 16 when 4 is used as the other operand. So if we have 16 here, and we put either A, multiplication here, or B, addition here, this is the operand. and 4 is the other operand. And so, if we put addition or multiplication here, the result will be greater than 16. Multiplication and addition will cause an increase in the operand, which is 16. However, the result that we have there is smaller than 16. For a smaller number, it cannot be that we added 4 or multiplied by 4. The correct operation must be one of the others. If we subtract 4 from 16, what will be the result? I heard Jerry saying 12. If you are sure, Jerry, you need to speak up. So there we have 16 objects, and we need to subtract 4. What is the result?
12.
The result is 12, and the option is C. So option C is correct. The other operators are not correct, but we will take a look at their results. 16 multiplied by 4 is equal to?
64.
16 plus 4 is equal to?
20.
16 divided by 4 is equal to?
4.
Right. So, if you are solving a problem like this one, you do not have to go through so much explanation and so much fundamental principles. You may just go straight ahead and determine the answer. But we are doing a mathematics audio-visual resource. Therefore, we are making sure that all ends are tied. John gets deep dollars per day pocket money for 5 school days. How much pocket money in dollars does he get in all these 5 days? So John gets D dollars per day pocket money for how many days? 5 days. How much pocket money in dollars does he get in all of these 5 days? Per. Whenever we see the word per or each in mathematics, it's usually a clue that we need to divide. But Jerry said that we need to multiply. Well, he's looking at it from a different perspective, because it is saying per, and at the same time we need to find the result of all of these 5 days together. So if it is per and we need all of the days together, it should not mean that we should divide. But usually if we see per and each in mathematics, it's usually a clue that we need to divide. But this is when we want to find the amount of each. So let us say that again. Whenever we see the word per or each in a mathematics problem, it is usually a clue that we need to divide. But this is when we want to find the amount of each. So if we have the amount of each, like what we have in this particular case, and we want to find the amount overall, Jerry said that we should actually multiply, and he is right. But let us see how this can be proven to make perfect sense. All of these 5 days. In this case, we are not finding the amount of each, but the overall amount. We therefore do the opposite of division, which is multiplication. The correct answer is option A. The correct answer is option A. Multiply. If we need the amount of all of the days, there is no way that it can be smaller than the amount for 1 day. It has to be more. Why multiply instead of add. So we know that we cannot divide because we have the amount per day or the amount for one day. And what we are trying to find is the amount for all of these 5 days. So the amount for all of these 5 days could not possibly be equal to the amount for one day divided by 5. That is not sensible at all. And why is it that we do not add? Because D is the amount of money and 5 is the number of days. It is not practical to add money and days. Also, it is out of character with the nature of this problem. So addition would not work. Per all of these 5 days. Be practical. There are how many school days in a week, Jerry?
5.
There are 5 school days in a week. What are they?
Monday, Tuesday, Wednesday, Thursday, and Friday.
And Friday. Let's say that John eats 2 chairs each day. Monday, Tuesday, Wednesday, Thursday, and Friday. 5 school days. Let's say John eats 2 chairs every day. How many chairs did he eat in all?
14. 10.
So we have 10 chairs in all because they are 5 days. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So John ate 2 chairs each day for 5 days. He would have eaten all of 10 chairs. With 2 chairs per day for 5 days, how did we arrive at 10 chairs? We may solve another operation problem. So, with 2 chairs per day for 5 days, how did we arrive at 10 chairs? And Jerry is saying that we should multiply. We may solve another operation problem. The operands are 2 and 5. Which operation will give a result of 10? Which operation will give a result of 10? And that is multiplication. Students may glance at the word per and immediately divide. However, students need to take a good look at the problem in order to determine exactly what is required. So we are using a smaller and more practical version of the problem to determine whether we should add, subtract, multiply, or divide. Because if we have 2 chairs per day for 5 days, we end up with 10 chairs. With the 2 and the 5, how do we arrive at 10? Only by multiplication. Therefore, multiplication is the correct answer. And we need to multiply the D dollars by the 5 school days in order to tell the amount of money that he had for all of the 5 days. Peter has X marbles. John has twice or 2 times as many marbles as Peter. Together they have 96 marbles. How many marbles does Peter have? How many marbles does Peter have? Let us say that again. Peter has X marbles. John has twice as many or 2 times as many marbles as Peter. Together they have 96 marbles. How many marbles does Peter have? And students at this level, I am happy to see a problem worded like this, because some students try to solve this problem and they keep going around and around and around in circle and never get to the correct answer. This is a standard problem for not only grade 4 numeracy, it is a standard problem for GSAT, and not only for primary, but it is also a standard problem for high school. When one gets a certain number or amount and the other gets twice as many or twice as much, what is our situation? And we will go to the most minute detail of the fundamental principles that may be used to solve this problem. So Peter had X, 2 times as many marbles as Peter. Let Peter's X marbles be how many marbles, Jerry? 2 marbles. So let us say that Peter has 2 marbles. John has twice as many marbles as Peter. What is twice as many as 2?
4.
4. So John has 4 marbles. How many X's do we have in all?
3.
Right. So that is the key in solving the problem. Because when one person gets X or 2, the other gets twice as many. The other will get 2X. So we have how many X's here?
3.
Right. So some students end up with 2 X's, divide 96 by 2, and we get 48. But if we divide 96 by 3, what do we get?
32.
Right. So there we have 1, 2, 3 occurrences of X. How many marbles in all?
6.
6 marbles. Peter has how many?
2.
The total is 3 times Peter's marbles. 2 times 3 is equal to 6. And we can see that playing out here, where we have Peter has 2 marbles. John has twice as many. So he has 4. So we have X here, we have another X, and we have another X. In all, we have 3X. How many X's do we have in all? There are 3 of them. 3 X's means 3X in algebra. In this case, it is 3 times Peter's marble. How many marbles in all? So we see Peter has 2 marbles, but the number of marbles that we have in all is 6. So if Peter has 2 marbles, the total amount will represent how many times Peter's marbles? We have 2 marbles for Peter, 6 marbles in all. The total is 3 times Peter's marbles. If one has X and the other has twice X, then in all they have 3X, which is 3 times X. We will apply this to 96 marbles. So I hope that we understand that when one person has a certain number or amount and the other has twice, then in all they have 3. So one has a particular amount and then the other has twice as many or twice as much, then together they all have 3 of the original number or amount. So if one has X and the other has twice X, then in all they have 3X, which is 3 times X. We will apply this to 96 marbles. If Peter has X marbles and John has twice as many as Peter, then John has 2 times as many marbles as Peter, and that will be 2x. So Peter has x and John has 2x, because that's twice as many marbles as Peter. We have already shown that they have what? 3x marbles together. But if we add x and 2x, what will we get?
3x.
Right, so they have 3x marbles together. The number of marbles that 3x represents is?
90.
Right, so 3x represents 96, which is the total number of marbles. What number do we multiply by 3? And the result is 96. The number must be smaller than 96. We need to divide 96 by 3. Or, solving the equation, we need to eliminate 3 from that left-hand side. It is multiplying x, so we need to eliminate it by the opposite of multiplication, which is division. And keep the equation balanced by dividing by 3 on the other side also. So, we have 3x is equal to 96. We need to solve that. We need to eliminate this 3 from the left-hand side. We will do so by dividing by 3. We need to treat each side of an equation equally. So if we divide one side by 3, we need to divide the other side by 3 also. When we do that, 3 will be eliminated from the left-hand side, and on the right-hand side, we have 96 divided by 3. So on the left-hand side, the 3 will be eliminated, and on the right-hand side, we will have 96 divided by 3, and there we have it. When dividing, it is good to have the multiplication table of the number that you are dividing by in your mind. So if you are dividing by 3, what times table should you have in your mind, Jerry?
3.
Your 3 times table. So there is our 3 times table. And we say 3 into 9.
3 times.
Because 3 is 9. 3 into 9 will go 3 times. 3 into 6.
2 times.
3 2's 6. So 3 into 6 will be
2 times.
2 times. The correct answer is therefore option
A.
Division is the opposite of multiplication. If you know your multiplication table, then apply it in reverse when you are dividing. The table shows the favorite sports of some boys. Which 2 sports are liked by the same number of children? Which sports are liked by the same number of children? Which 2 sports are liked by the same number of children? When tallying data, the diagonal stroke is also counted. Each group that looks like this represents 5. When counting items that are tallied, count by 5 for each group of 5, then add the extras. So this we have 1, 2, 3, 4, 5. So this represents 5. 4 vertical stroke and the diagonal stroke. So that's 5. So when we are counting, we do not have to be sitting down and wondering, how many this? 1, 2, 3, 4, 5. Or when we do this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No. We know just by looking that it represents 5. So we have that is 10 plus 2, and that is
12.
And then the other will be what?
17.
Right, 17. Very quickly, because it will be what? 3 5s, 15 plus 2, and that will be 17. And Jerry is pointing on the screen already saying the correct answer is option B, which represents basketball and football. And as a matter of fact, he discovered that very quickly, and he could have been quicker in arriving at the answer because we do not need to count the strokes or the items that we have there in order to determine the correct answer. But let us make use of our principle that when we have to count items in a tally table, then we do not have to take 165 days in order to do that. So when we do that, we just have 5 plus 1, and that is equal to 6. And the other one will be 5, 10, 15 plus 2,
17.
which is also 17. So which two sports are liked by the same number of children? The sport that has the same number of children are basketball and football, and represented by option B, as say Jerry. If items in a tally table are organized in the way that they should, then the ones with equal number must have rows of equal length. So as long as it is arranged in the way that it should be organized in a systematic way. So it should be well organized and not sloppy, but everything is done in the correct order, then we do not need to count them. We just look at the length of what we have here, or we may say the width, if you please, but we will say the items that we have here, as long as they are organized in the correct manner, then the width of the data should tell us which ones are liked by the same number of students, the ones that we have equal lengths of. So if the lengths are equal, then that will represent the ones that are liked by equal number of students. And that will be represented by, as we can see, the length of the arrows already, that football and basketball are the ones. The ones with equal length rows are football and basketball. They are liked by the same number of children. As a matter of fact, we do not need to know the number of each in order to know that they have equal numbers. All we need to do is just glance and see the ones that are equal in length or width. Then we know that those are the ones. More. The word more gives the idea of extra or surplus. How many more children like basketball than cricket? How many more children like basketball than cricket?
10. Yeah. 11.
Right. So the word more gives the idea of extra or surplus. In order to determine how much more one number is greater than the other, we need to subtract 1 from the other. So we have 17, and from 17 we subtract 6. 7 minus 6 is equal to?
1.
And 1 minus 0 is equal to? 1. The number of them is 11, and it is represented by option A. The word more suggests addition, but that is if you are given more. In order to find by how much one number is greater than the other, we subtract. If we have a number repeated a number of times, we multiply. But we divide if we need to tell one number is how many times another. So we cannot just look at a particular statement and jump to conclusion, because jumping to conclusion is bad exercise. If we see each in a problem, we do not go straight ahead and divide. We will divide if we need the amount or number of each. But if we have each and we want to find the total amount or number, then we have to multiply. And if we have a number repeated a number of times, we multiply. But we divide if we need to tell one number is how many times another. So there we have our 17 students. There we have the 17 children who like basketball. Let us ask the 6 who like cricket to step forward. How many like cricket?
6.
Let us ask the 6 of them to step forward. We can already see that one is 11 more than the other. Can we see that?
Yes.
Because when we cause them to step forward, we see that these are the ones that we are talking about, and these are the ones that are left. So there is no doubt that the surplus is 11. Mary has 6 apples. Roy has 2 apples more than Mary. How many apples does Roy have? Mary has 6 apples. Roy has 2 apples more than Mary. How many apples does Roy have, Jerry?
4.
Let's go again. Mary has 6 apples. Roy has 2 apples more than Mary, because Mary has 6.
Roy has
2 more than Mary. How many apples does Roy have?
8.
8 is correct. But let us say more again. This is saying that Roy's number is greater, and it is greater by 2. We therefore need to add.
Add.
Right. So we therefore need to add. Mary has 10 apples. Roy has 7. How many more apples than Roy does Mary have?
21.
Mary has 10 apples. Roy has 7. How many more apples than Roy does Mary have?
20.
Right. How many more apples than Roy does Mary have? Mary has how many? 10.
10.
Roy has how many?
7.
7. How many more than Roy does Mary have? Mary has more. The question is, how many more than Roy? Mary has more already. Therefore, in order to tell how many more we need to subtract. So Mary just has 3 more apples than Roy. What about this one? So what we are discussing here is that when we say more, we do not necessarily mean that we should add. Because if we need to find, in this particular case, how many apples does Roy have? If Roy has 2 apples more. If Roy has 2 more, how many apples does Roy have? So we add the 2. But we know that Mary has 10 and Roy has 7. So how many more that represents, then we need to subtract. And in this particular case, John, that's what we have there. John has 5 sweets. Pam has 7 times as many sweets as John. How many sweets does Pam have? John has how many sweets? 5. Pam has 7 times as many sweets as John. How many sweets does Pam have? 7 times as many. Pam surely has more. Also, when we have a number occurring a given number of times, we multiply in order to get the total number. But what about this question? Sam has 24 cupcakes and Loy has 6. How many times the number of cupcakes that Loy has does Sam have? How many times? So there we have our problem here. That one has what? 7 times as many. In this particular case, we multiply. But the same word is being used, times. How many times the number of cupcakes that Loy has does Sam have? In this particular case, we divide. We already know that the number of cupcakes that Sam has is a certain number of times the number that Loy has. In order to find how many times, we divide. So we need to analyze or take a look at the requirement of the problem before, when we see times, we just go straight ahead and multiply. It may mean, depending on what the times is in reference to in the problem, it may mean that we need to divide. A bag has 3 red, 4 blue, 5 yellow, and 6 black balls. If one ball is taken out, which color is it most likely to be? So a bag has 3 red, 4 blue, 5 yellow, and 6 black balls. If one ball is taken out, which color is it most likely to be? At present, the bag is empty. Let us place the balls inside of the bag. So there we go. Place them inside of the bag. If one ball is taken out, which color is it most likely to be? By looking, what would you say, Jerry? Is it most likely to be?
Black.
Okay, it is most likely to be black, and that is represented by which option?
D.
Option D. It might be very plain that if you pick up a ball, a black one has the greatest chance of being selected. Why? Look at the number of each.
The largest number of balls.
Right, because it has the largest number of balls. Because it has the greatest number, the one of which there is the greatest number has the greatest chance, or is the most likely to be selected. Option D is correct. So because it has the greatest number, it is the one that is most likely to be selected. That is the black. Some may say that the yellow is most likely because it is bright and easier to see. But that is just an optical illusion. The one with the greatest number is the most likely. And you will have situations like this in real life where, because of how things appear, you imagine that they are the most favorable. But it is a matter of just how it appears. And that is what we call an optical illusion, where looks may be deceiving. So you may be deceived by what it looks like. What it looks like is much different from what it is in actuality. Let us continue with problem number 47. The following table shows the price board in a school snack shop. What is the total cost for 2 buns, 1 cheese, and a small drink? The word is total. The most important word that we have there is total. We need to find the total cost, so we need to add the values according to the statement of the problem. Adding will give us the total. As long as we are required to find the total, it means that we are required to add. For the 2 buns, we have a choice. Either multiply the price by 2 before adding, or add it twice. We will add it twice instead of adding another phase to the solution. What does that mean? It means that if we multiply and then add, it means that we have 1 phase of multiplying and then 1 phase of addition. But if we add it twice in the total, then we will only need to just add. So just eliminate the phase of multiplication by including the bun twice. There we go. So for 2 buns, we put the price of the bun twice. So that's the price of the bun, and we put it twice because there are 2 buns. There is only a single cheese. We will have only 1 occurrence of the price. A single cheese. 1 occurrence of that one. And a small drink. A small drink means 1 small drink. The price of the drink will also have 1 occurrence. So instead of multiplying at one stage and then go to another page to add, we just put them together and just add them. By what? By including the price of the bun twice in the sum. Finish up by underlining and including the addition sign. So we will add this way. We will finish up by adding, and when we are adding, we need to include the addition sign, and we need to draw our line below which the total will be placed. So when we are adding, we notice that what we have here, we have a lot of repetitions. Because of the repetitions, we will use the multiplication to simplify our process. So instead of saying 5 plus 5 plus 5 plus 6, we are adding how many 5s here?
3.
Right. So in adding, we will take advantage of repeated digits. For example, 3 5 means 3 times 5, which is equal to 15. So we have 3 bracket 5, which means 3 5s, which will be 15. So when we are adding, what do we have there? We had
2 5s 10.
right, 2 5s 10. And what do we do?
Put down the 0, carry the 1.
Put the 0 down and carry 1 to the column of more or greater significance. So we put 0 down and carry 1 to the next column. Do we have any repetition there, Jerry?
Yes.
What?
7 and 7.
So we have what there then? 2 7s
14.
plus 1 plus 5, and that will give us
20.
right. So that is as easy as it gets. So when we have repetition, we use the multiplication. Of course, we have 7 occurring 2 times, so that's 2 times 7. Write down 0 and carry 2 to the next column. Okay, so Jerry is already identifying the answer. So in this one, what do we say? We have how many occurrences of 5?
We can go to the 5, that column yet until we put down the decimal point.
Right, so Jerry is insisting that we have to put the decimal point before we move on to the next column. So vertically align the point with the others. So there we go. Putting the decimal point down. Vertically aligning the decimal point with the others. And what do we say? How many occurrences of 5 we have there?
3.
3 5s.
15.
So we have 15 plus 2 plus 6, and that is equal to?
23.
Let me see if Jerry is paying attention on this occasion. 3 and carry 2. How many occurrences of 2 do we have in the next column, Jerry?
We have 4.
Right, so the 2 that was carried over is also one occurrence of 2. So we have 4 2s
8.
plus 1.
9.
Right, and he told me long ago that the correct answer is 93. But I am sure that Jerry will not leave the answer like that. What?
We're dealing with money, so you have to put down the dollar sign.
Alright, so we are dealing with money, so we include the dollar sign. So we are dealing in currency, include the dollar sign. And the correct answer is $93. This part is not multiple choice, Jerry. This part is essay type. Harry has a ball of thick string 6 meters long. He needs to put this string along the edge of a rectangular tabletop. And the rectangular tabletop is shown in the diagram. Does he have enough string? That is our question. And notice that I am emphasizing the H's because there is a story about a boy who went to the teacher and said, Harry took the hammer and hit me in my head. And the teacher would say, emphasize your H's, your ignorant ass. Alright. So I am making sure that I do not make the same mistake. So Harry has a ball of thick string 6 meters long. He needs to put his string along the edge of a rectangular tabletop shown in the diagram. Does he have enough string? How do we know that? The tabletop is rectangular. Opposite sides of a rectangle are parallel and equal. Right, they are parallel and equal in length. So along the edge of a rectangular tabletop, and the rectangular tabletop has opposite sides that are equal in length, and they are also parallel. So what do? We have 30, and opposite to 30 we also have 30 centimeters. Opposite to the 70 centimeters we have 70 centimeters. If we find the perimeter of the tabletop and it is smaller than the length of the string, then he has enough string. Let us find the perimeter of the tabletop. So when we find the perimeter of the tabletop, if that result is less than the length of the string, then we know that he has enough string. Let's go. The perimeter P is the distance around. Let us find the distance around the top of the table. So P is equal to 70 plus 30 plus 70 plus 30. What is 70 plus 30, Jerry?
100.
Therefore, it is clear that the total perimeter will be
200.
right. So that is how you operate in mathematics. You don't count your fingers and saying 7, 8, 9, and so on. You see 7 and you see 3, that's 10. You see 70 and you see 30, that's 100. You have it occurring twice, that's 200. It's as easy as that. Jerry is on top of his game. 200 centimeters. Does he have enough string, Jerry?
No. Yes.
Why yes? Because this 6 meters, how many centimeters, Jerry?
600.
Right. So this 6 meters that we have there represents 600 centimeters. And how many centimeters do we have here?
200.
Therefore, does he have enough string?
Yes.
Okay. Surely he has enough strings because 200 centimeters equal to 2 meters, while he has as much as 6 meters, which is equal to 600 centimeters of string. So for sure, he has enough. So let us look. We have 100 centimeters, and that is equal to
1 meter.
Convert 200 centimeter to meter. If we have 100 centimeter equal to 1 meter, 200 centimeter will be how many meters?
2 meters.
It's as easy as that. The transfer is easy. It is clear that when we are converting from the centimeter side to the meter side, we need to reduce the number by 2 places of decimal, which is the same as dividing by 100. So since we have 100, we have 1. 200, we also reduce this by 2 places of decimal, which is the same as dividing by 100. So 200 divided by 100, the result is 2. Convert 6 meters to centimeters. If we have 6 meters, how many centimeters will we have, Jerry?
600 centimeters.
Right. Just by writing an equation like that, the transfer or the conversion is very simple. So when we are converting from the meter side to the centimeter side, we need to increase the number by 2 places of decimal, which is the same as multiplying by 100. All we need to do is maintain the consistency in the table. It is easy to convert from one unit to the other as long as we know how many of one makes the other. We may then think of the conversion as a transference from one side of a table to the other. Using the first row as a guide, all that we need to do is maintain the consistency in the table, which is what we did. So if we have a number on this side like 500 centimeters, that will be 5 meters. And if we have 3 meters here, let's say we have 4 meters here, it will be 400 centimeters. The perimeter was found to be 200 centimeters. The length of the string was given as 6 meters. We know the conversion factor already. There it is, 100 centimeters equal 1 meter. We may convert any way that we want. We may convert the centimeter to meter or the meter to centimeter. Since we have done it both ways already, let us just write the numbers down again. So we did the conversion already. And I am saying, if you had that problem to solve, Jerry, the length of the string is given in meters, and the perimeter of the table was given in
centimeters.
Right. So in order that they may meet, we may choose to convert our centimeters to meter or our meter to centimeter. Which one is more convenient to us? After doing whichever conversion you find convenient, the comparison will be the same whether you compare in centimeter or you compare in
meters.
Okay. Irrespective of the one that you choose, you will discover that the length of the string is greater than the perimeter of the tabletop. He therefore has enough string. So if we compare these two, the length of the string is greater than the perimeter. And if we come over here, the length of the string is still greater than the perimeter. So we know that he has enough string. The tabletop is rectangular. As usual, for a rectangle, we will call the long side the
Length.
and the short side the
Width.
and some call it the breadth. So the length and width, or some will call it the length and the breadth. Let us find its perimeter P, which is the distance around the top of the table. So let us go again. So we have P is equal to length plus,
Width.
then plus what?
Length.
Plus,
Width.
right. So the perimeter is length plus width plus length plus width. We have two occurrences of length. And how many occurrences of width do we have, Jerry?
2.
The perimeter may therefore be written as twice L plus twice W, because we have two lengths and we have two widths. So the perimeter may be written as 2L plus 2W. Later on in mathematics, you will learn to factorize and see that twice length plus twice width may also be written as twice the sum of length and width. Although you have not gone through those algebraic processes, it is still logical to you. So let us write that down. 2 times the sum of the length and the width. So the perimeter may be given as 2 times the sum of the length and the width, or 2 lengths plus 2 widths. Let us do that again. Remember the perimeter in which we added the edges of the tabletop individually. Can you remember that? Of course you do. P is equal to 70
Plus 30 plus 70 plus 30.
Jerry is going very quickly. And that is equal to 200 centimeters. It is the same thing. So we will not have to go through a million miles in order to get it right. So let us now show that we will get the same result if we use perimeter is equal to 2 length plus 2 width. Right, perimeter is equal to 2 length plus 2 width. And what is the length?
The length
Of the tabletop is?
70.
Right, and the width is?
30.
Right, so 2 times 70 plus 2 times 30. What is 2 times 70, Jerry?
140.
140. And what is 2 times 30, Jerry?
60.
Right. So we have 140 plus 60, and that is equal to
200 centimeters.
200 centimeters, says Jerry, which is the same that we had before. So show now that 2 times the sum of length and width will also work. P is equal to 2 times the sum of length and width. So it's 2 times the sum of the length and the width. The length is 70 and the width is?
30.
What is 70 plus 30, Jerry?
100.
So 2 times 100 will give you?
200.
Right. If the formulae are correct, then they should all yield the correct result. We are therefore sure that they are all correct. Irrespective of what formula we use, we got the same result. The table below shows the number of 4 types of cars in a car park. Use the grid to draw a graph of this information. So the grid. When a graph is to be drawn on a grid, as we have been instructed to do, there are some basic features that it must have. When you are drawing a graph on a grid, there are some features that it must have. The axes are very important. The graph has to have what? Axes. And axes is the word that is the plural of axis. The axes are very important, especially for quantity data. Data that give numbers, that's quantity. When the data is in number, what goes on the axis is very important. They tell which quantity is associated with a certain direction. They also show how the quantities are distributed for each unit of length along the axis. So, when we have the axis, we know which axis tell which quantity is associated with which direction. They also show how the quantities are distributed for each unit of length along the axis. Each axis must have a label that tells us the quantity or type that it is associated with. So, each axis must have a label that tells us the quantity or type that it is associated with. Grid. The horizontal axis that goes across is usually called the x-axis. On this occasion, it is associated with the types of cars. The vertical axis that goes up is called the y-axis. It is associated with number of cars on this occasion. Students may be instructed which item of data must be placed on which axis. And by the way, students, data is not a singular word. Data is a plural word. The singular for data is datum. So we have one datum and we have many data. So students may be instructed which item of data must be placed on which axis. On the horizontal axis, the data is given in types of cars. In this particular case, it is classified as a categorical data form. So, it is type of cars that is classified as categorical data, because we do not have numbers here, but we just have types of car. So the cars fall in their respective categories. Therefore, the data on the horizontal axis in this particular case is classified as categorical data. Categorical data. On the vertical axis, there are numbers. The type of data is called quantitative data because we have numbers here. This is quantitative data. For quantitative data, we may tell how many or how much, and it is represented in numbers. The scale that is used on an axis. The scale tells us what length of the axis is associated with a fixed number of units of the quantity. A scale that is used on the axis, the scale tells us what length of the axis is associated with a fixed number of units of the quantity. So let us take a look at this one. If the length that we have indicated is 1 centimeter, then the scale on the vertical axis is 1 centimeter to 2 units. So if this length is actually 1 centimeter, then the scale is 1 centimeter to 2 units. So 1 centimeter is used for 2 cars. The scale on the horizontal axis could be 2 centimeters to 1 unit. Although it is not quantitative on the horizontal axis, because we are sure that there is no quantity here, but we only have types of car, which causes the data on the horizontal axis to be categorical data. But I am saying maybe in a particular situation, or if what we had here was 2 centimeters, we could say that what? 2 centimeters are representing 1 unit. So 2 centimeters to 1 unit on the horizontal axis is only a possible scale, as scales are not usually given with categorical data. The cars are categorized according to their types on the x-axis. So I am saying, we are just saying that is a possible scale. 2 centimeters to 1 unit is a possible scale. But scales are not usually associated with categorical data as we have there, because the cars are not in reference to numbers, but in reference to types of cars. And that causes the data to be categorical instead of being quantitative. We have taken a look at the axes, their labels and scales. We may draw the graph with less challenge. So we will draw the graph now. But we may do so with what? Less challenge. Why? Because we know what are axes, what is a scale, and we also know the significance of labeling the axes. Honda. How many Honda do we have, Jerry?
4.
We have 4 Hondas. Go to Honda and the number of item is
4.
the bar will therefore have a height of how many units?
4.
Right, so there we have Honda and the height is
4.
4. So the bar will be 4 units. What do we do next, Jerry?
Go to Toyota.
Right, so go to Toyota and how many Toyotas do we have?
10.
There are 10 Toyotas. The height of the bar is
10.
10 units. So that's the height of the bar and that's the bar. And we then move to
Suzuki.
Suzuki. And Suzuki has how many?
7.
7. So the height will be how many units, Jerry?
7 units.
And notice that we are going up by 2 each time, right?
Yes.
So the 7 will be halfway between 6 and 8. So there are 7 Suzukis. 7 is halfway between 6 and 8. So the bar, or the height of the bar, will take us between 6 and 8. Not just between 6 and 8, but exactly halfway between 6 and 8. And finally, what do we have?
Nissan.
And how many of them?
2.
So the bar will have a height of 2 units, which is one of those blocks. So there we have our table. And from the table, we have arrived at our graph. Students should understand the scale in 2 ways. A, use the scale to number the axes, and B, use the scale when putting information on the graph. Well, there's another way, that you will use the scale and is extracting information from the graph. You have to be consistent with the scale that you have there. So we have use the scale to number the axes, use the scale when putting information on the graph, and the C could be use the scale when you are extracting information from the graph.